today we are going to graph parent functions and their transformations. One skill you should have getting through college algebra and college trigonometry is, as I've said before, you should be able to solve any equation that you see or inequality. Second of all, you should be able to graph any function that you see. Today and Monday's lesson is possibly the most important to you being able to have that skill. So today we're going to do what I refer to as easier ones, and then on Monday we will do more difficult examples. So a graph of y equals 2 is a horizontal line. Y equals c. So y equals some constant is an example of a linear function. You can also have one that looks like this, y equals x. And then you can transform that by, say, adding 2 to the end or multiplying by negative 2/3. We all know about slope and y-intercepts, and that transforms it. So when I say transform, I mean that we will take these shapes, we will move them up, down, left, and right. We will also tilt them, do all sorts of things to change their shape and the direction of the function. Okay. So we also have absolute value function. Y equals absolute value of x. So all we do is we take the previous function and we make it positive. So you can't have any part of it going below the x-axis, so it goes above the x-axis, like so. We're not going to do greatest integer function. I'm tired of it. Power functions. Y is equal to x squared. What does that look like? A parabola. A parabola is above the x-axis. Why? Why does it stay above the x-axis? Because when you square it, it's positive. When you square a number, it becomes positive. How about when you cube a number? Are cube numbers always positive? No, they're not. If you cube a negative, you get a negative. So therefore, it has some negative values. When you take something to the fourth power, do you get a positive or negative? Positive. I try to draw it where it's a little bit flatter toward the bottom. That's what happens. It kind of flattens out towards 0 and gets steeper on the sides. But I'm not going to be very critical as I look at your graphs. And then y equals x to the fifth. Do you think you can have negative values for that? Yeah. And so that will be even a little bit steeper. We'll go up. When you take something to the fifth power, it gets bigger more quickly. For example, 2 to the third is 8. Well, 8's big. It's not as big as 2 to the fifth, which is 32. So it gets bigger much more quickly. Root functions. Y is equal to the square root of x. What does that look like? And as you look at the square root of x, you recognize the domain. You can't plug in what kind of numbers? Negative. And furthermore, we say that you can't get out negatives. So the square root function, a lot of times when you see square root, you say square root of 9 is plus or minus 3. We only list the positive one because if you listed the negative one, you would get the bottom half of that. And is that a function? No. So that's why we always talk about the principal root or the positive root. Obviously, if you change the equation to y squared is equal to x, you took the square root of both sides, then you would have to list the positive and negative because you would be solving for a variable. Different scenario. Okay, cube root. Can you take a cube root of negatives and you get a negative. So it looks somewhat similar to the cubic from above. Yeah. How about the fourth root of x? Do you think that'll look like the first one or the second one? Yipper dupper. And fifth root of x. I like this stuff because it's, you get tired of dealing with lines all the time. It's like, give me something more interesting. So other root functions. Um, let's look at y equals x to the 3 over 2 power. And what that means is we take x and we cube it. You could write it like this: the square root of x to the third. When you cube, or when you take the square root of something, you can't take the square root of a negative. And a negative to the third power will be a negative. So are you allowed to plug in any negative values? No. And so when you graph it, you'll actually get just the positive side. Whereas if you look at this graph, that means y is equal to the cube root of x squared. Can you square negative numbers? Yes. And when you square a negative number, you'll get a. So all of the outputs will be positive. You can plug in negatives, but you'll always get out a positive. This looks like a bird. I call it the bird function. It's my favorite. One of my favorites. I've got a lot of favorites. What, Sarah? You can say it. You can say it. What's your favorite function? You don't have one exactly, and you need to come up with one. Okay? What do you like? You don't even know what the greatest integer function looks like. You can't be your favorite. Don't judge the looks. Okay, I like it. I I would show you, if we had time, I'll show you second semester. I will show you what's called a barcode function. And if you don't think that that's awesome, then yeah. Actually, yeah, it looks just like. You want to see it right now? Pause it? Why? Yeah, they want to see it. If they don't want to, they can fast forward. Press the button, lazies. Oh. All right. Watch. Now, you're not going to be impressed right away, and I get that. So, when I graph this, it doesn't look very impressive, but okay. All right. I need to try to stay above the line here, because otherwise I'm gonna make some mean comments. So I encourage you to push your mind a little bit further and understand that what value can't you have for x? 0. So obviously something funky when you look at the graph, something crazy happens at 0, right? Do you see that? So in fact, I'm going to zoom. I'm going to zoom in. I'm going to zoom in right on that spot. You still don't like it. You see that the function has what we call hidden behavior. You don't see it right away until you get really close, right? Go, 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 go. Scan it, baby. Yeah, let's do it. Like that's impressive, isn't it? Yeah, okay. You know what's really cool? You could zoom in an infinite more times. It would look different every stinking time. Yeah, exactly. I agree. Yeah, exactly. Try it work. See, Sarah, you like that one. You don't like my bird function. Okay, well, you pick out your favorite function and you bring it back on Monday, okay? All right. Yeah, function. There you go. All right. Reciprocal functions are a little bit different. What value can't you plug in for 0? No. What? All right. It's called vertical asymptote. All right. So if there's a value that you can't plug into a rational function like that, many times you're going to get what we call vertical asymptote. All right. Now, in this case, you also have a horizontal asymptote, and an asymptote is it's an imaginary line that the graph approaches, but it never actually touches. Now, we do have a vertical one here because the graph can never have a value 0. However, I also want you to know this. I'm sorry, you can never plug in 0. There's an output that the graph can never achieve as well. For example, let's think about this. What number would you plug in for x to have an output of 1? 1. What value would you plug in to get an output of 1/2? What value would you plug in to get an output of 3? 1/3. What value would you plug in to get value of 10? 1/10. What value would you plug in to get an output of 0? You can't. There's no number you could plug in and get 0 out. So there's an input you can never have, but there's also an output that you can never have as well. And if I plug in a negative, 1 over a negative, will that be negative or positive? Be negative. So on the negative side, it is below the x-axis. And on the positive side, it is above the x-axis. And so that's the shape that we get. That's a reciprocal function. It's the kind of the, you know, it's a parent functions where a lot of them come from. So if we change this and we look at y is equal to 1 over x squared, that is extremely similar. It does have a vertical and horizontal asymptote at 0 again. But what's different? If you square it, the output will be positive. So therefore, it will stay above the x-axis the entire time. This page of notes that you just filled out, you need to commit to memory. You need to remember what all these shapes look like. You'll be much quicker through your work, and we will practice it so that you will hopefully remember it even better. I will just say that your challenge moving forward outside of my class will be when a professor moves to the board and says, look at this function and says what it looks like. Where did you get that? Well, this is the library of functions where we get probably 95% of the ones that you look at in calculus. Let's move on. We'll complete this side, and I'm going to give you your homework assignment. Yep. Every day. So you had this in your Algebra 2 course where you talked about transforming functions. And here we have f of x is equal to g of x plus k. And that will provide what we call a vertical shift. And here's the key. I've taught this many times, and I've seen people be confused. And the quicker that people grasp onto this idea, the less confused they are. If it's on the outside, it is a vertical shift. If it is on the inside, it affects it horizontally. Outside, vertical. Inside, horizontal. So you see that the plus k and the minus k are on the outside. If you see a plus k, it's going to move up k units. The entire graph. Every single point will move up exactly k units. If you see minus k, will move it down k units. If we had something like this, f of x is equal to g of x minus c, or x plus c. Is the c on the inside or the outside? It's on the inside, so therefore it affects it horizontally. Now this is where it's a little bit different. A minus c, as you see that, do you know if it will shift it to the right c units or to the left c units? It will shift it to the right. You remember when we did this? X minus 3 quantity squared plus y plus 2 quantity squared is equal to 100. What shape did that make? It was a circle. Where was the center of that circle? 3, negative 2. Opposite of what you think. Horizontal shift right here, opposite of what you think. So when it's on the inside, it's opposite of what you think. So therefore, if you see a minus c like that, it will be to the right. C units. And if you see it on the, if you see a plus, it would be left. C units. When it comes down to it, this is what I believe is your best option. Solve the inside equal to 0. And what I mean is this. If you have x, whoops, sorry. That shape is a parabola, but if you're wondering the horizontal shift, you don't think about plus 3 or minus 3. You solve the inside equal to 0. When you solve the inside equal to 0, what do you get for x? Negative 3 halves. So since it's negative, it moves to the left. Negative 3 halves. So as opposed to looking at a minus or a plus side, I just think about solving the inside and then shifting it that number of units. I think that that's your most helpful option. Okay, let's do some examples. Identify the parent function. What does the parent function look like for the first example? Parabola. So I would encourage you to draw this light on your sheet and then draw the actual graph dark. What kind of transformation do we have? Is it on the outside or inside? Outside, so is it vertical or horizontal? Vertical, so it's going to be down 3. So I shift the entire graph down 3. Done and done. Piece of cake upside down. What does the next parent function look like? Yep, very good. It's like that. Is it on the inside or outside? The transformation. Inside, so horizontal or vertical? Horizontal. Solve the inside equal to 0 and you get 4. X minus 4 equals 0, you get 4. So it moves 4 units to the right. What does the next shape look like? The thing. Yep, looks like the thing. Very good. Should watch the movie The Thing. You know? So x plus 3 cubed minus 2. Technically, you should apply your transformations in the order of operations in which they occur. That means if you were to plug a number in for x, you would first add 3. You wouldn't subtract 2. So therefore, we're going to look at the horizontal shift. As a horizontal, what's the horizontal shift going to be? 3 units to the left. So I go back 3, and then after I go back 3, I go down 2 because the minus 2 is on the outside. So this this spot on the graph moves over and down to that spot right there. So draw the same shape, but that central point is located right there. So this spot, that middle part of the graph where it does that bend, I'm going to move it back 3 and down 2. So I will draw the same thing now. So if I were to pick up the red graph, whoop, ooh, don't throw your markers at people. You know, so it sits right there then. All right, and then the last one. What does the shape make? A V? Very good. And what are my transformations? Right 4 and down 3. Got it? Okay, now let's talk about reflections. If it's on the outside, it's vertical. If it's on the inside, it's horizontal. So if you have a function f of x equals negative g of x, that negative is on the outside. The negative is on the outside, it affects it vertically. So it will flip it over which axis? Yep, a vertical flip will be over the x-axis. Flip over x-axis. The horizontal reflection, f of x is equal to g of negative x. If the negative is on the inside, it will flip it over y-axis. So the first parent function, square root of x, looks like this. Is the negative on the outside or the inside? It's on the outside, so will it affect it vertically or horizontally? Vertically, so it's going to take it and flip it over the x-axis. The next one is the negative on the inside or outside? Inside. And here's where I say, slow down, okay? A lot of people get confused with this type of problem, problems after this that have a negative on the inside. And here's what my encouragement to you is. Don't think about, you know, it's like, well, does it move positive 3 units or negative 3 units? And when do you do the reflection? What do you do? I don't see problems written like that very often. And when you see things written in calculus, we want to deal with the problems as we would see them. So here's what I'm trying to tell you. First of all, is there a horizontal shift? Yes. What would you plug in to get 0? 3. So therefore, we move 3 units to the right. Second of all, when you square it out, when you FOIL it out, are you going to end up with a positive x squared or a negative x squared? Positive. So we'll end up going up or will it go down? We'll go up. I think that's the best way to handle negatives when they're on the inside. Look at the shift, and then when you multiply it out, what would you get? Now, there are a couple exceptions with the root functions, but we'll deal with those as the time comes, okay? So, this one right here, is there a horizontal shift? What would you plug in to get 0? 1. Oh, this is where I stopped drawing last time. They got mad at me. So, yep, there's our parent function. Our parent function for this one is a cubic. So, yeah, you would plug in 1 to get 0. So it shifts to the right 1 unit. And then the plus 4 makes it go up 4. Tell me, when you would cube this all the way out and multiply and add, would you end up getting a positive x to the third or a negative x to the third? A negative x to the third, right? X times x will give it x to the third, then you have that negative at the end. So will it start down and finish up, or will it start up and finish down? Start up and finish down. We're going to draw the same shape. This point right there where it kind of changes direction, so to speak, is now going to be up there. Right 1, up 4, flipped upside down. And then finally the last one. What would you plug in to get 0? Yep, our parent function is at V shape, and you would plug in 0 to get, or plug in 5 to get 0. And there's no real way that we can work out, a square root, but the negative on the outside, what's that going to do? Flip it over the, yeah. The only time I would want you to really look at a horizontal reflection when it's on the inside is when we have a square root function, and we will talk about that. So, all right, I'm going to pause, and we're going to look at a worksheet. Okay, so here we are. That's the parent function. Is the -3 on the outside or the inside? Outside, so will it affect it horizontally or vertically? Vertically, so it moves it down 3 units. Okay, and the domain, for all these examples I give to you, the domain is all real numbers, except for the root functions or the reciprocal functions. That's what we looked at the other day in our assignments. You can plug any value you want in for x and you're going to get an output. Anybody identify what the range is here? So the range is the possible outputs. Will you get out a value of -10 at some point? How about -4? Yep, how about 2? How about 10? Yeah, negative infinity to positive infinity, or all real numbers. So whether you write it like all real numbers or whether you write negative infinity to positive infinity is acceptable. Okay. Let's go to one where you do not have domain of all real numbers, and it's a little bit more complicated. Please look at the one that I have starred up there. We have y equals negative root of x minus 4. Is the -4 on the inside or outside? Inside. So is it horizontal or vertical? What would you plug in to make 0? 4. So I move it 4 units. I'll draw the parent function in blue. This is going to move 4 units over. Then the negative is going to do what? Flip it over the x-axis. So that's the shape. Domain, whether you want to look algebraically at the original equation or whether you want to look at the graph is up to you. I will admit, folks, when I look at domain and range of functions, I not only try to look at the equation, I also try to picture in my mind what the graph is. Can you plug in values over here? What's the first value you can plug in? 4. 4 to what? As far as range is concerned, will the function go down here someday? Yep. What's the last value you'll get? 0. And flip it over. Let's just look at this one. Parent function looks like that. What's the shift? 3 to the right, up 2, and then what's the negative in front do? Domain? all real numbers. It's just the root functions on this assignment we have to worry about. Then the range. That's that. I like it a lot. Okay, question. No. Do what I did, and that's sufficient. 2 pages a day, 4 pages on Monday. So go ahead, and you got about 7 minutes.